Today, I will be presenting the topic of neural architecture search, NAS, and entity quantification with DeepHyper. Same project as yesterday, DeepHyper, initiated by Prasanna Balaprakash in 2018, where the goal is to automate the development of machine learning algorithms to support scientific application. DeepHyper is an open source project, and you can find it online at this address for the documentation. Myself, Romain, I am a finishing master student, and I will be starting a PhD this year. DeepHyper is architected around three main components: search algorithms, ensemble, and workflows. Yesterday, we talked about hyperparameter search and Bayesian optimization for hyperparameter search. Today, we will be talking about how to use neural architecture search for ensemble to build better entity quantification. DeepHyper is already installed on ALCF systems such as Theta and Theta GPU, and the module is accessible with this command. After loading the module in your environment, don't forget to activate the base Conda environment to access the correct Python interpreter. Let's talk a bit about neural networks. When you do classification, for example, here between cats and dogs, from images, you have an output probability distribution, and depending on your training data, if you have other example, for example, with noise or with different styles that were not in your training data, you accept this probability distribution to reflect this growing uncertainty between the classification. For example, with these two data, you should have bigger uncertainty. Now you have another use case where you can have horse data, elephant, or tiger that are not at all in the label of your training data. Here, this is called out of distribution, and you would like the distribution basically to predict something like a uniform to show total uncertainty and to reflect the fact that this data is unknown to the model. It was not shown during the learning phase. We have two major forms of uncertainty. One is called aleatoric, the other epistemic. Aleatoric uncertainty is reflected in the noise of the data. It can actually also be named intrinsic random noise. Epistemic uncertainty represents the uncertainty of choosing a model to generate the corresponding data. Therefore, in areas where you don't have any data, this epistemic uncertainty explodes if your model doesn't have any strong hypothesis. Now, neural search is composed of three components: a search space, a search algorithm, and an evaluation strategy. The search space represents all the possible neural networks that you want to explore. The search algorithm is a search optimization strategy. For example, yesterday we saw Bayesian optimization, but you can also have random search or genetic algorithms. Finally, the evaluation strategy represents how each candidate neural network is trained and how the performance metric that you want to maximize is computed. For example, if you compute the accuracy on the validation set or the MSE. Therefore, in neural search, we need to define a search space. How does it work? In DeepHyper, the search space inputs and outputs are fixed by the problem reflected in your data. You want to do a classification from an input query X with a fixed dimension, for example, and you predict a classification or a regression with some variables that are fixed. Within these inputs and outputs, you will have a direct acyclic graph, which reflects this time different nodes represented in blue, where each node reflects a choice between different operations. So, contrary to chaos layers, where only one operation is possible, here the first node reflects a choice between identity, dense layer with 15 neurons and identity, dense layer with 15 neurons and switch activation function, etc. Therefore, neural active search consists in exploring in a discrete search space where each candidate reflects a choice for all these discrete variables that are described in blue in this diagram. You do a choice for N1, for SC1, SC2, N2, SC3. The SC nodes here represent skip connections. For example, you want to create a residual connections that start from the input and will be input again, skipping the first node to the second node. Usually, in neural active search, the hyperparameters are kept constant. Here, I mean the learning rate, the batch size, and the optimizer, for example. They are fixed for all trained neural networks. However, if we remind the two kinds of hyperparameters what we saw yesterday, which are algorithm hyperparameters and model hyperparameters, the one on the left reflects how we estimate or train a neural network, and the one on the right reflects the neural network architecture. Do you want a multi-layer perceptron? Do you want a recurrent neural network or a convolution? Which operation are you choosing in this architecture? In our case, we will take advantage of these two types of hyperparameters to optimize both jointly. Why is it important? Because if you keep algorithm hyperparameter fixed, it can be very penalizing for your training. For example, a bad learning rate can be very penalizing for all types of neural architecture. This is why you optimize both in same times. And how do we do that? So we call this joint hyperparameter and architecture search. If we remind the training data of yesterday denoted as T for the lower level problem, this time we minimize the error on the training data with respect to the architecture and the hyperparameters that are fixed, and we look for the optimal set of weights. And the upper level on the validation data, this time we look for the best architecture and hyperparameters, and for each of them, we have the optimal trained weights. Now that we know how to generate models with good hyperparameters and good architectures, we can execute the search and, for example, generate 500 models during the search. Not all of them will be good, so we will select some of them to do a deep ensemble. Selection of K models for deep ensemble with uncertainty quantification. On the left is represented a catalog of models that was generated by DeepHyper during a joint hyperparameter and neural architecture search. Each of these neural networks is outputting a probability distribution. In the case of classification, the probability distribution is represented by the probability of each class. So it's what you have, for example, after a softmax layer. You have the probability of a given class Y given X, the input. Now we select K models to build this deep ensemble. For example, we select the first one, the fourth one, and again the first one. These models are generally selected by order of performance. But in some strategy, it's not the case. It can build a mix of different models to find complementary predictions. The ensemble now reflects a new mixture of distribution, because again, each neural network outputs a distribution, and here you create an ensemble by mixing this distribution and build a new one. Now that we know how to have this ensemble distribution, we can decompose its uncertainty in two types of uncertainty that we described before, which are the aleatoric uncertainty and the epistemic uncertainty. Aleatoric, which represents noise in the data, epistemic, which represents uncertainty of choosing the right model to predict what we want. If we denote sigma I square for the variance predicted by the ensemble, the decomposition is the following. The two sigma theta and mu of theta, so variance with respect to theta, a neural network, and mean with respect to theta, and same neural network, given an input query, These two quantities are actually predicted by each neural network present in the ensemble. The aleatoric uncertainty corresponds to the mean of the predicted variance, and the epistemic to the variance of the mean prediction. Epistemic uncertainty easily represents the disagreement between neural networks which are part of the ensemble. What we want neural networks to predict very similar things when they are taught the same thing. But if they are not taught about something, we want them to disagree a lot. That's basically what we want. On the left, we marginalize and average the estimated noise of each neural network to be more robust and more general. Now that we have seen this method, I can redirect you to the tutorial of DeepHyper when we're going to be finished with this workshop, where you're going to find different tutorials to dive more into the detail of these methodologies, and also to learn how to execute this on the Theta and Theta GPU supercomputers. And today, we are going to dive in a hands-on session called From Neural Architecture Search to Automated Deep Ensemble with Uncertainty Quantification. This notebook contains a lot of materials that you will not probably not be able to run in today's session. But if you are interested, you will be able to continue afterward, and do not hesitate, of course, to ask questions during the hands-on session on the Slack. Now, if you have questions, before starting the hands-on session, I would like to answer them. So don't hesitate to interact now.
I have a question.
Yes, please go ahead.
How do you define the stopping criteria? When should the model or the architecture search be stopped?
So the stopping criteria in the HPC setting is often a wall time. When you run on the resources of ALCF, you will request, for example, 1 hour of computation. And therefore, if you run neural search within this hour of computation, generally, the stopping criteria is the time. We want to generate as many architecture within this whole time. However, so there is no stopping criteria in terms of convergence. For example, if the metrics that you want to optimize become stable and you don't improve, let's say, for 100 iterations, by default, there is no stopping criteria on that. However, you can easily define one within the framework with a custom callback.
Has this been used on any of the data sets? Like, do you have results on how long it takes to find a good architecture, like ImageNet or something like that?
So we executed DeepHyper on different problems related to cancer data, relating to atmospheric prediction for different layers of the atmosphere. And generally, we managed to have good architectures in the whole time of a few hours, maximum 6 hours. On Theta KNL, which is a CPU-only machine, you use a lot of nodes, but you maintain this whole time, and you will use between 128 nodes, which is actually the minimum allocation, and 256 nodes usually for 3 to 6 hours. And for Theta GPU, we are usually able to use, for example, 8 nodes. So you have 8 times 8 GPUs, so 64 GPUs. And you can run this easily also for 6 hours to have good neural architectures.
Okay. Yeah. Thanks.
Any other question? Okay. So if there is no question, I will start showing the interactive notebook. I encourage you to join the channel on the Slack called the O3 Distributed HyperOpt. This is where the information are located for this hands-on session. Also, don't forget to pull the latest change of the SDL AI workshop repo to have the good version of the tutorial. So let me open my navigator. So this is the GitHub repo that you have to pull. And on this repo, you have to go in SDL AI workshop, O3 distributed hyperopt, and then O2 NAS and more. You should find this README file from neural active search to automate dependable within quantification. And in this file is described how to execute on your local laptop, how to execute on Theta GPU, and how to execute also on Theta KNL. So for both Theta GPU and Theta KNL, the idea is to just ask for one node iteratively for 1 hour. Then you will initiate a Jupyter notebook. When you will initiate this command, it will both output a URL that you will copy and paste into your navigator. And you will also have a SSH command that you will copy paste to your shell to forward the connection to this notebook that is executed on ALCF. And after executing the second command, SSH, the notebook will be accessible on your local machine. This notebook is heavier to run than the one presented yesterday. So I will not run it all in front of you. I will show the already available output and explain them to you. Again, don't hesitate to ask any question and tell us about the issue you face when running this tutorial. So we will go through how to detect the GPU or not, how to start the Ray cluster, which is used as a backend to distribute tasks in DeepHyper. We'll see the data we are using, how to pre-process them, how to apply a baseline neural network on it, because it's always good to have a baseline machine learning algorithm before applying hyperparameter search or neural active search to make sure we are framing the problem correctly and there is no big issue inside the data. Then we define a space of neural network architecture. We run the optimization. We define the NAS problem, create an evaluator object, run the neural active search, and then have the uncertainty estimate part. So when you run Jupyter notebooks, DeepHyper is also using asynchronous I/O, async I/O, and by design in Python, it's not possible to run 2 async I/O loops in the same context. Therefore, we use this package, nest async I/O for nested async I/O, and we patch this async I/O loop to be able to run DeepHyper in a notebook. Then after this, so this should be already installed in the module on Theta, and you should not have issue with this, but it's important to run this. Then we have the import section, and we export the 2 variables. One is to reduce the verbosity of TensorFlow, which is quite annoying, and the other one is quite important on GPUs. It's enabling a much faster training. TF XLA enable XLA device. So it's important to export these variables often. After we have a little cell that detects how many GPUs are available. Here you can see that it's written 7 GPUs. It was run on a node of Theta GPU. Why not 8 GPUs? Because when we use Ray and when we import TensorFlow in the main process, 1 GPU is actually initialized and logged by TensorFlow. And therefore, to distribute the task, we use the 7 other GPUs. Otherwise, we have errors with this locking of the GPU. Then we start a Ray. So again, Ray is a backend that needs to be started or initialized before executing DeepHyper. If you don't do it, it's done by DeepHyper, but the limitation is that it will just use the resources of the local node. So when you start Ray before DeepHyper, the goal is to allocate resources on the different nodes of a system, like Theta GPU, have the cluster initialized on all these nodes, and then connect the DeepHyper to it, which will be aware of the different nodes where to distribute the task. Now that we have the infrastructure set up, we dive into the synthetic dataset that we will use. This dataset is a sinus function with some noise. It's an artificial dataset used to visualize the behavior of uncertainty with deep neural networks. So here there is a picture of this dataset. It's quite a small dataset to be able to run the tutorial in a feasible time. We have the test data or the underlying true model, okay, in gray, which is sampled regularly on the x-axis. And then we sample two cloud-off points on the left and on the right. On the left, we have a noise of 0.25, if I'm not wrong. And on the right, we have a noise of 1. This is to see if we are able to generate neural networks and ensembles that can learn the noise differently on the left and the right, basically. The blue points correspond to training data and red points to validation data. So we'll try to learn this, and the goal at the end will be to have good estimation of the noise on the left and on the right. And in areas where we don't have data, we want the epistemic uncertainty to explode to represent the fact that the model is lacking knowledge in this area. Now that we have data, we pre-process the data with a standard scaling, which means that for the input data and for the output data, we remove the mean and we scale the standard deviation to 1. It's important because neural network weight initialization is made so that the propagation of your gradient and the variance is quite stable if your input data is standardized. Now for the baseline neural network, it's a very simple neural network where we have our input and output fixed of size 1. And we have 2 layers with 200 neurons and ReLU activation function. It's quite classic. Then we use the Adam optimizer and we minimize for this training the mean squared error. So in this case, as you can notice, there is no uncertainty quantification estimate at all. So here we train the model and you have the output, and then we plot the training for the validation and the training data. And we can see that they follow each other. So it's good because when they don't follow each other, it often means that you have some overfitting. So here the behavior is quite coherent. And if we want to visualize a prediction of our neural network, don't forget to, so you do the prediction of your neural network, then you reverse the scaling. So you multiply by your variance and you add your mean that you remove, basically. And here we plot the output and we can see the behavior of the model in area in gray where we have data. We have a quite good fit on the left and the right. And in area where we don't have data, we don't have any quantification, but sadly this learning is very poor. So this is what was expected because there is no assumption. With the currently used model, there is no assumption under the current basis of function that is used. Now we are going to learn how to define a neural architecture search space. To do so, we are going to use 2 objects. One is called K-search space. It stands for Keras search space. It's the direct acyclic graph that I presented in the slide before. And we're going to wrap this key search space in an object called space factory, just made to ease the sharing of search space between people and make the API a bit more streamlined. And inside this direct acyclic graph, we're going to define 2 types of nodes. One type is called variable nodes, is where we want to give the possibility to choose between different layers, different operations for the architecture search. And one other type, it's called constant nodes. For example, it's for the input, the output, which is fixed and not searched by the algorithm. So this is the cell doing this. we import the two objects to create the search space. We import the constant and variable nodes. After we import specific operations, so the search space is composed of nodes, and nodes, variable nodes, we give them a list of operation, not layer, but operation. It's a different object specific to DeepHyper. And here we import specific operations for residual skip connection, the zero operation, the connect, and an operation made to merge different input connections of neurons. So the zero connections, it means I don't want to connect, and connect means I want to connect. Another operation is identity, where you want to give the possibility to choose the identity operation, which means not do anything. So if you have two nodes where you give identity and a dense layer, and you both choose identity, you have zero layer in your neural network. Finally, you have the operation function that we import from DeepHyper, which is very practical. It helps you create operation directly from Keras layers. So any Keras layer can be used in DeepHyper. That's the big advantage. The difference is that you will be able to define all your Keras layers in the search space. However, none of the tensors will be allocated. So you will not have explosive memory when exploding memory when defining your search space. It will be done just when the neural network will be created and chosen. Then we use the space factory. The space factory, so we call it here a regression factory because we have a regression search space. And this is how it works. We have this build operation that we have to implement. It takes the input shape and output shape of your data and other arguments that you can define as the user. Then you initiate your direct acyclic graph with your input and output shape and call it SS, which stands for search space here. You build the intermediate layer possibilities, and you build your output, and you output this search space. How does the intermediate subgraph works? In this case, we create a queue of size 3 to collect each operation, each node that we create, Therefore, later we will be able to go through this queue and create possible residual correction from it. It's like a buffer where we input each variable node that we create. The maximum size of this buffer is 3. So each time you add, it push the last one out. And you create skip connection from this. Therefore, for each new node, you look over the 3 previous nodes and you create skip connection from them, possibly. So for example, we create a dense variable node here with dense operation with different units and activation function. Then we create a merging operator that will accept all possible residual connections. And for each node in this anchor point list, we create possible residual connections with the zero operator and the connect to one of these previous nodes. For example, for the dense variable node, this is how it works. We use the function add up to add operations to the variable node. Here we add identity, and we add different number of units between step 16 and 16 times 16. And we add the different activation functions that you saw above, which is about 10 different activation functions. So as you can see, a good idea sometimes is to order some operations by meaningful order. Why? Because some search, like Bayesian search, work better when you have ordered discrete variables. However, for genetic algorithm, it's often useless to do this. Once you created your search space, you wrap it here in a function, which will be used to be passed to the problem definition later. Let's visualize possible neural networks. So I use my regression factory that I just defined with my input and output shape of 1. And I plot 4 random generation of model from this search space. And this is what I have. I have this neural network on the left, this second neural network, and you can see you have different layers, different connections, and you have 2 other models. And again, you can keep generating them. It's quite fun. And you will quickly see that it will be hard to define all of this network by hand. The advantage of exploring all this type of connection is that residual collection have a big impact on the shape of your loss function when you do optimization. And because we are in a non-convex case of optimization, adding skip connection in specific ways can sometimes help the optimization. So you will be able to produce networks with less weight, better convergence, and better generalization. Next, now that we know how to define the neural architecture search space, we define the neural architecture problem. It's a bit more automated than the hyperparameter search because in neural search, you don't really need to define how to train the network. It's provided by DeepHyper. Therefore, you define how to load your data. You provide your load data that return training and validation data. You define how to pre-process your data. You define the search space, and you define a set of hyperparameters that will automatically be used. Your loss, possible metrics, and the objective that you want to maximize. So here we want to maximize the negative of the mean squared error on the validation set. And it's also automatically using the one at the last epoch of training. Am I going too fast, or do you have questions? Is it okay? Some feedback would be great from the audience.
Seed equaling none right there, is that just the default? Look, not explicit.
The what, sorry?
Seed, where it says seed equals none.
CD plus none.
Seed equals none, the second line.
Yes,
yeah.
Seed is because no random seed was defined. So when you create a program, you can define the random seeds to fix the random generator. So here none is defined. It means if you re-execute the search many times, you will have different results. And if you fix a seed, if you re-execute the search different times, you should have a similar result.
Thanks.
Also in DeepHyper, here you can see that you can define the Keras callbacks. Here we use the early stopping strategy. And this is very practical and very important because it reminds me of the question that was asked at the end of the slides presentation. It helps you stop each training as soon as it's become useless. And therefore, it's maximize the possibility of training neural networks in a given hold time. This is a strategy to be more efficient that is important to use. Now that we define the evaluator, the problem, neural architecture problem, we're going to define the evaluator object. The evaluator object in DeepHyper is the way we abstract the different backend infrastructure on which we want to distribute the computation. So for example, you have an evaluator to do neural search with sub-processes on your local laptop, and you have an evaluator to use Ray that can help you execute on big systems or clusters, such as ALCF system, Titan, Theta GPU. So here we create an evaluator. Depending if we detect or not GPU, we create an evaluator that use these GPUs or not. By default, we create an evaluator with only one worker, and each task uses only one worker. We also add a callback to this evaluator, logger callback, that will output some information during the search. So when we execute this, we have the creation of one worker evaluator if I run it on my local laptop. And if you run it on Theta GPU, you will have 7 workers, one for each GPU on one node. Once the evaluator is created, you need to bind it to a function that will receive a configuration of neural network and hyperparameters that will load your data, train the neural network, and compute a performance metric. We provide you with such a function, which is called DeepHyper NAS run alpha. Here we rename it as run NAS. And now we can set up the search. All search algorithms in DeepHyper have a similar interface. First, you need to instantiate the search with a problem definition. Here, a neural active search problem definition, and then an evaluator object, which is binded with a remote function to distribute. Other arguments correspond to the parameter of the search. So once we have the search, the random search, we can search for a number of evaluations that is fixed. It's my choice here. I choose 10 evaluation. I execute it, and I have some feedbacks with the performance. And my best performance is minus 0.32 here. And another possibility, if you have a hold time that is fixed, for example, if you use 1 hour at ALCF, it will be to use the timeout method, where you pass a time in second to the search to generate as many architecture in a given timeout, and it will stop afterward. So the goal here is to compare different algorithms for neural active search. First one is random. The second is a genetic algorithm. However, it's important to note that this genetic algorithm is random until you reach 100 iterations, because it needs to generate a population of 100 individuals before optimizing. And so comparing these two search with 10 iteration is not really interesting. So if you are interested, you can run it, for example, for 300 or 400 iteration in your local machine, and you will see the difference of performance and what is the interest of using a better optimization rather than random, because it's always important to note that random search becomes more and more competitive when you increase the amount of available resources, right? When you can do full exploration on a big system, such as the system available at ALCF, it becomes interesting to use random search because it's really fast to generate new configurations, and you can actually explore the space efficiently. But on a local laptop, you want to use more efficient search because you will never be able to do all this computation. So after, you have a little plot that will show you the best objective found so far since the beginning of the search and compare both search. And you have the output returned by the DeepHyper search, which correspond to a data frame composed of argsec variable. Argsec is the embedding of each architecture. So as I said during the slide presentation, for each variable node of your search space, you choose an operation. This corresponds to a discrete choice represented by an integer here. So each index in this list represents a variable node by order of creation in the search space. After you have the identifier of the architecture, it corresponds to the order of creation, the objective return, the time when it finished, and the duration of the training of the neural network. So here we plot the best model from the search. So we reuse the factory we defined previously. We get the best model from the random search with IMAX here. And we use it to collect this argsec and pass it to the factory to output the model. And it looks like this. We have input, dense, 2 dense layers. We merge with addition here. And we continue. It's quite short, it's quite shallow. Finally, we reach the uncertainty estimate steps. To do uncertainty quantification with DeepHyper, we rely on TensorFlow probability, which provide a similar interface to TensorFlow Keras. that we can use with NAS. So everything in TensorFlow probability, you can use it with DeepHyper as well. That's the advantage. In uncertainty quantification, instead of minimizing the mean squared error, we want to maximize the quality of probability distribution, and therefore we want to maximize the log likelihood of the real data. So we predict a probability distribution, and what is the likelihood of having this data for this predicted probability distribution. And maximizing the log likelihood corresponds to minimizing the negative log likelihood. So this is what we define here, a custom loss function. And we redefine the similar baseline network, but this time we have two outputs because we are going to predict the mean estimate and the variance with respect to the data, so to the single variable that we output. And we pass this to a distribution lambda. It's help you define different type of distribution. Here we define a normal distribution. We assume that the output variable follow a Gaussian. And we pass the first neurons to be the mean, and we pass the second neuron to be the variance, and we put a constraint, a positive constraint on this variance to ease the optimization. So we pass this custom loss function, the optimizer is the same, the fitting, the number of epochs is the same, and we continue. Do not hesitate to interrupt if anything is unclear. I will be happy to comment. It's made the session is easier for that. Or if you have broad questions about why is it useful, etc. So here I plot the training loss and the validation loss. Again, we see that both they follow each other, so you don't have overfitting, so it's quite good. And this time we are gonna, so this time it's not the MSE, it's the negative log likelihood again. We're gonna output what is predicted by the neural network. You will see that it's a bit different. So this time we have a mean prediction in a plain line here in orange, and we have a variance, a predicted variance. You can see that in area where we have data, it's not always a good prediction actually. Even if we use the same number of epochs and same batch size, etc., same neural network architecture actually, and this is where the issue comes from. We use the same neural networks, we change a bit the setting, and the architecture now is performing very poorly. So that's interesting. However, we can see that on the left, it's kind of minimizing the variance, so it starts to learn the noise here. And also you can notice that the behavior of the uncertainty is very bad in areas where we don't have data. It's not at all informative. What we would like here in the middle is the uncertainty to explode, or at least to increase, so that we envelop the underlying model, and at least we know that it becomes uncertain here because we don't have data. But here you don't have any of this information, it's just bad. So this example is made to show you this. And remember that in the first phase, the fitting of the model was very good. If I show you again the baseline neural network and the estimation and the predicted, here you see that it overlaps much better the mean estimate. So that's interesting. It's good to know that you, when you minimize negative log likelihood, if you assume that the standard deviation of your output variable is 1, you will end up with minimizing the mean squared error. So the MSE loss and the negative log likelihood loss are linked when the variance of the predicted variance is constant and equal to 1. Okay, let's continue. So we were here, we just saw this. How to solve this? So we are going to use neural architecture search. But first, we're gonna try a very classical technique that is advised. It's to use the same neural network architecture, retrain it many times with different random weight initialization, build an ensemble out of it to have good uncertainty estimate. So this is what we do. We use the baseline architecture with uncertainty estimate, and we just generate a few candidates that we save, and we use them to build an ensemble. So here we select, we retrain it 10 times, we put this in our ensemble. How to build an ensemble with DeepHyper? We have this API with uncertainty quantification bagging ensemble regressor or classifier. You just have to have a saved model from Keras as H5 format. You indicate the path to this directory where your model are saved. After you pass the loss you want to minimize, you give the size of your ensemble. Here you can link it with the Ray backend to distribute the creation of your ensemble to be more efficient when you have big models and you want to use several GPUs in the same time. It's going to distribute the inference of the models and the selection of the model. And you choose a selection strategy. We provide different selection strategy. Here I choose top K. Basically, it means that I choose a model, the 5 best model in the model random init directory to build my ensemble. So I fit my ensemble on my validation data to have an estimate of generalization again. I have my 5 models that are selected. The name of the files are output here, and I output the estimate. So you can see that here you have a better mean estimate on the left, a better uncertainty estimate. On the right, it's still not good at all. And you can see something else. Now that we have an ensemble of neural networks and not just one neural network, we actually have in yellow the aleatoric estimation of uncertainty and the epistemic estimation. So aleatoric reflects the noise in the data, and epistemic the uncertainty in the model. So here it's very bad because we would like the aleatoric uncertainty to match exactly the noise in our data, which is about 0.25 variance on the left and 1 on the right. And it's not the case. And also the epistemic uncertainty, the component, is not increasing. So again, we are not happy with this strategy. To decompose this uncertainty of the ensemble, we use the law of total variance for people who are interested in the mathematics. Finally, now that we have seen that this was not working properly with a single neural network and with an ensemble of randomly initialized neural network, we're going to do something different. We're going to use neural architecture search jointly with hyperparameter search to generate a catalog of n models so that we wish to generate high-performing models. And after, from this catalog of high-performing models, we select a subset called an ensemble to have better uncertainty estimate. So again, we build a neural architecture search space, this time with uncertainty quantification. So it's almost same as the first one. The only difference is the output here. The output, which is instead of just being a dense layer, it's a dense layer with 2 neurons for the mean and variance estimate. And after we have this probabilistic layer, normal distribution that we showed in the baseline. Otherwise, it's same as the first example. And for the neural architecture search problem, we are going to do almost the same, but for all hyperparameters, instead of fixing a constant, we give a possibilities. For example, before we fixed the batch size to 4, and now the batch size is a possible value between 1 and 32. For the learning rate, it's between 0.0001 and 0.1 with a log uniform prior distribution to allow equal sampling between small learning rate and bigger learning rate. The log uniform is very important when you have a range of values with different order of magnitude, and you want to sample equally on the whole range. Otherwise, if you don't use log uniform, you will have a lot more samples of big learning rates rather than the small ones. Okay, for the optimizer, we give a list of possibilities between many optimizers. And even for the patients of reduction of the learning rate and early stopping, we give some possibilities. So it's quite interesting, quite fancy. Instead of breaking our head to fixing some hyperparameters and trying them again and again, we give possibilities and the algorithm is gonna find the good configuration for us. In addition, we save all the networks that are explored with this model checkpoints. We define the negative log likelihood as the loss, and we maximize the minus of the validation loss again. Okay, and now we execute the search, which is called AGEVO, which stands for Aging Evolution with Bayesian Optimization, which operates both on hyperparameters and neural architecture. We execute this search to generate 400 neural networks. And once we generated these 400 neural networks, we're going to build again an ensemble with uncertainty quantification estimate. And here we select 100 models in our ensemble for the purpose of diversity and the purpose of showing that the model can be distributed correctly. Even if you select 100 models, which is quite a lot, it will work fine. So we have the list of all models. And here, again, we predict the output uncertainty estimate, and you see that now it's much better. You are able to learn better the mean estimate on the left in the orange line here, and on the right. In addition of the mean estimate, you are also able to learn a good aleatoric uncertainty because you see that on the left, it's mostly yellow. On the right, where you have data, it's also mostly yellow. However, in area where you don't have data, the uncertainty is in majority orange. Okay, so it means that you have a good estimation of epistemic uncertainty, and here you clearly see that your model is telling you, I don't know, more and more up to the middle, and again reducing. It doesn't know what to do here. It doesn't know what to do on the border, and this is very informative, and this is what we wanted. And this is what we can do with different type of architecture, classification, and regression data. Now that the tutorial presentation is over, if you have any questions, please go ahead. No question? Was it interesting?
It was. Thank you.
Okay.
There's a lot of information in there. Even I personally will have to go through it after the workshop.
Yes, I wanted to provide you with a lot of materials that you could explore afterward. If you have to remind something, is you can automate all the search of neural architecture and hyperparameters to reduce the burden of searching them by hand and retraining models. And in addition, when you use automated search with DeepHyper, you can valorize the generated and explored models to automatically build afterward ensembles of this explored neural network and have uncertainty quantification estimates, which can be very important for scientific applications to share models and to have meaningful predictions. That's the message of this presentation.